Hello my friends and welcome back to the You Can Do TV channel. The scrapping of cars and feeding whole cars to shredders is a crucial part of the metal recycling process. It begins with the use of specialized material handlers designed for scrap handling, which plays a vital role in feeding entire vehicles into large shredders for further processing. These machines are essential for efficiently dismantling and recycling old cars, conserving natural resources, and reducing waste in landfills. Material handler for scrap. Material handlers for scrap are heavy-duty machines equipped with various attachments, such as grapples, shears, or magnets, designed specifically for handling large volumes of scrap metal. In the automotive recycling industry, these machines are primarily used to pick up whole cars and feed them into shredders. The machines typically have long, articulated booms that allow for extended reach and excellent maneuverability, which is crucial when dealing with entire vehicles. Modern material handlers are built for efficiency and safety. They can be equipped with fuel-efficient engines, offering up to 200 kilowatts of power, providing the strength necessary to lift and maneuver whole cars, which can weigh anywhere between 1,000 kilograms to 1,500 kilograms. Additionally, some advanced models feature operator-friendly controls, including joysticks, cameras, and automation systems that make the process faster and safer. The process of feeding whole cars to shredders. Once a car is deemed unsuitable for further use, it is sent to a scrapyard where material handlers, typically weighing between 30 to 90 tons, lift the entire vehicle and place it on a conveyor system leading to an industrial shredder. The speed and size of the handler are critical here, as the machine must carefully feed the shredder while maintaining throughput and safety. Large industrial shredders are designed to handle a wide variety of materials and are specifically built to process whole cars. These shredders have a high throughput capacity, ranging from 80 to 200 tons per hour, depending on the model. The shredders break the car down into smaller, manageable pieces of scrap metal by using rotating hammers or knives powered by motors with horsepower ratings between 2,000 and 10,000 horsepower.
The pre-shredding process at Iveco is a crucial step in the recycling of end-of-life vehicles. Before shredding, all ELVs must undergo mandatory depollution, where hazardous components like tires, bumpers, batteries, and fluids are safely removed. This is done using the ERV breaker, which ensures vehicles are fully depolluted before processing. Upon arrival, ELVs undergo a visual inspection and acceptance procedure before being directed to the pre-shredder. The pre-shredding phase eliminates potential hazards such as gas bottles, tanks, and other non-usable materials, enhancing safety and efficiency for the final shredding stage. The pre-shredder uses slow compression to handle volatile items like LPG tanks and fuel containers, optimizing safety. Once pre-shredded, materials proceed to the shredder, where ferrous metals are recovered magnetically, and non-ferrous metals and plastics are sorted using advanced technology. A copper wire stripper is a tool or machine used to remove insulation from electrical wire and then cut it into small pieces to recover clean copper. It is commonly used in recycling works and motors, allowing the user to effectively strip a variety of wire sizes for reuse or sale of valuable copper core. The MT-XL retread was developed to meet the demand for retreading the newly designed 29.5 R29 OTR tire. Marangoni began with a thorough analysis to ensure the casing's integrity and suitability. The old tread is removed through buffing. Given the tire's harsh previous use, minor damages are repaired. The tire is rebuilt using 3 layers of compound, replicating a new tire. Due to its size, curing is done in an autoclave. Using the Recaflex system, Marangoni grooves the tread in various custom designs. Each tire undergoes a detailed inspection, both visually and through chirography, to ensure inner structural quality. Once verified, the retreaded tire is shipped back to the customer, offering a reliable and sustainable second life. The Schelkman procured retreading system ensures high-quality retreaded tires through a precise and controlled process. The worn tire is first inspected and buffed to remove old tread. A high-performance procured tread is then applied using advanced adhesives. The tire is enclosed in a rubber envelope and placed in a curing chamber, where heat and pressure bond the new tread. This method delivers durability, safety, and consistent performance, extending tire life while reducing environmental impact and operating costs. A mining truck is loaded onto a special trailer and transported by one trucks, depending on its size, to a mining center near Kalama. The D33 dragline was prepared for transport by Mamoet at Beckville's B area. Heavy equipment was used to lift and secure the dragline. Once stabilized, it began its journey toward the Liberty Mine. During the move, the dragline got stuck on soft ground. Mamoet responded by placing large steel plates under the tracks to restore mobility. After regaining traction, the dragline continued its route and successfully left the B area, heading toward its new location at the Liberty site. CNC trucks transport wind turbine blades up Baoding Mountain in Yunnan Province. The process begins with securely mounting each blade onto specialized windmill trailers. Drivers navigate narrow, winding roads with precision, often requiring coordination with escort vehicles. The trucks maintain low speeds for safety, especially on sharp turns and steep slopes. Upon reaching the mountaintop, the blades are carefully unloaded and prepared for installation at the wind farm site. The in-plant assembly of the SL 16,000 crawler crane at Uchimiya Transport and Machinery. The assembly begins with the preparation of the car body, the crane's main structural base. This component is positioned on leveled ground, and its crawler tracks are attached using hydraulic jacks and support stands to ensure stability. Following the base setup, the upper rotating structure, known as the superstructure, is hoisted and mounted onto the car body. This unit houses the operator's cab, engine, and control systems. Alignment is critical during this phase to ensure seamless rotation and operation. Next, the assembly team installs the gantry, a vertical framework that supports the boom and facilitates its movement. The gantry is carefully lifted and secured with attention to the hydraulic lines and mechanical linkages that control its motion. The boom assembly follows, starting with the boom foot, which is connected to the superstructure. Subsequent boom sections are added sequentially, each pinned and bolted securely. During this process, the boom hoist cables are threaded through sheaves and connected to the winch system, allowing for controlled raising and lowering of the boom. Counterweights are then installed to balance the crane during operation. These are mounted on the rear of the superstructure, with their weight and placement calculated based on the crane's load chart to ensure optimal stability. Finally, the hook block and load lines are attached, completing the mechanical assembly. Comprehensive system checks are conducted, including functional tests of the hoist, swing, and travel mechanisms, as well as safety systems like limit switches and emergency stops. Only after passing these tests is the crane deemed ready for operational deployment. This systematic assembly process ensures that the SL 16000 crawler crane is constructed to meet rigorous performance and safety standards, readying it for heavy lifting tasks in various industrial applications. The installation process involves a link belt 248 HSL 200-ton lattice crawler crane and a 248 H5 crane lifting bulb T bridge beams. Each beam, weighing 120,000 pounds and measuring 135 featuring 41.1 meters long, is hoisted 120 feet into the air. The cranes carefully position each beam onto the bridge supports. Precision alignment ensures structural integrity as part of the overpass construction in Phil Campbell, Alabama.
Benefits of scrapping cars through shredding. The shredding process allows for the separation of ferrous and non-ferrous metals, as well as other materials like plastics, rubber, and glass. After being shredded, the metal is sorted using powerful magnets to extract steel, while eddy current separators isolate aluminum and other non-ferrous metals. Typically, up to 75% of a car's material can be recycled, with about 60 to 65% of that being steel. The recycling of cars is not only environmentally friendly but also economically beneficial. By recycling steel, for instance, scrap yards reduce the need for mining raw iron ore, which cuts down on energy use. Recycling 1 ton of steel saves about 1.4 tons of iron ore, 0.8 tons of coal, and 0.3 tons of limestone. The Reb 22 ram baler is a powerful machine designed for high-volume tire baling and other recyclable materials. It operates with a shearing and baling force of 254 tons, offering unmatched versatility for processing a range of materials such as waste, fiber, non-ferrous metals, and tires. Equipped with either a 150 or 250 HP power unit, the baler provides high production rates while maintaining energy efficiency. The machine's unique features make it a leader in the recycling industry. It has an innovative shear blade designed to handle multiple materials without needing adjustments, which saves time and increases productivity. Additionally, the REB2's bale eject system and oversized release door allow for clean material transitions and maintain bale integrity, especially important for materials with memory like tires. The frame of the baler is constructed with strength and durability in mind, incorporating Hardox 450 replaceable liners in the compaction and extrusion chambers to withstand high hydraulic pressures. This ensures long-lasting performance even in demanding environments. With its high-pressure hydraulic system, The baler can produce bales measuring 45-inch width, 31-inch height, 62-inch length, handling large volumes of materials at impressive rates. For example, the baler 150 can process 37 tons of municipal solid waste per hour, while the baler 250 can handle up to 47 tons per hour. The system can also process a variety of other materials, including PET bottles, mixed plastics, aluminum cans, and insulated copper wire, making it a highly versatile baler. For additional efficiency, the baler can be outfitted with bagging and wrapping systems, especially beneficial for landfill applications, where it can increase material density and extend landfill life while reducing cover material requirements. Mining tires, some of the largest in the world at over 12 feet in diameter and weighing up to 8 tons, undergo a multi-step downsizing process. The process begins with the removal of the bead bundle from the sidewall of the tire. Next, a large industrial shear cuts the tire into large pieces, which are then further cut down to manageable sizes, weighing between 300 to 500 pounds. These sections are fed into a primary shredder for the first round of reduction, producing long strips. The strips are then processed again through a second primary shredder, reducing them further into 12 to 24-inch pieces. A third shredder, the chipping shredder, reduces these chunks even more. Any oversized chunks are recirculated for another pass through the shredder. The final tire chips are sorted using a vibrating screen deck. Properly sized material falls through the screen and moves onto the discharge conveyor, while oversized pieces are sent back for further shredding. The resulting tire chips are ready for resale or can be used in applications such as tire-derived fuel, TDF, or tire-derived aggregate, TDA, or processed further. The high-torque hybrid dual-shaft tire shredder from CM Shredders is a powerful and efficient machine designed for reducing, destroying, recycling, and processing tires and other materials. This shredder uses a dual-shaft system, which features high torque to efficiently tear through tough materials like tires. The machine can be fitted with either standard hook and shear knives or patented replaceable insert knives, depending on the specific application and requirements. One of the standout features of the hybrid shredder is its patented knife technology. These knives can be sharpened and reused up to 6 times, drastically reducing operational costs compared to traditional one-use knives. Additionally, the replaceable insert knives operate with minimal clearance between them, resulting in cleaner, more precise cuts with very little exposed steel wire. This precision is particularly important for industries where tire chips are used as fuel or in recycling applications, as clean-cut chips are more efficient and easier to process further. The biggest cost in operating a shredder is usually the maintenance and replacement of the knives. The innovative knife design allows for longer periods between replacements, quicker changes, and lower replacement costs. This contributes to a significantly lower total cost of ownership compared to other shredders. Furthermore, the machine produces rough tire shreds, which can be processed further into smaller chips, making it versatile for a wide range of applications like tire-derived aggregate or tire-derived fuel. In terms of capability, the hybrid dual-shaft shredders can handle a variety of tire sizes, from large off-road tires to smaller passenger tires. While larger tires may require pre-cutting or debeating, the shredder efficiently processes whole tires into rough shreds. These shreds can be used for disposal or fed into secondary shredders for more specific chip sizes required in high-volume production environments. The first stage of tire recycling involves the shredding of whole tires to reduce them into smaller pieces, making them easier to handle and process. Scrap tires are fed into a tire shredder equipped with a patented knife system, which performs the initial task of cutting the tires into strips. This process is known as a rough shred, and it reduces the tires into long, thin pieces that are not yet ready for final use. After the rough shred, the material is passed through a classifier that separates properly sized chips from oversized material. The larger pieces remain on top of the classifier and are sent back to the shredder for further processing, ensuring a consistent size of the material. Several passes through the shredder are typically required to achieve the desired size for the chips, which can then be sold as tire-derived aggregate, TDA, or tire-derived fuel, TDF. These products have various applications, including use in cement kilns, paper mills, and power plants where they are mixed with other fuels for cost savings. Once the tires have been reduced to the appropriate size, the next step is to separate the steel from the rubber. This stage uses specialized equipment known as a liberator, designed to effectively pull steel from the tire shreds. Pre-shredded tires, usually in pieces between 4 and 6 inches, serve as the feedstock for the liberator. As the tires are processed by the liberator, the steel is torn away from the rubber and discharged onto a vibrating conveyor. The vibrating motion loosens the mix of steel and rubber, which is then passed under a strong belt magnet. This magnet lifts the steel away, leaving wire-free rubber ready for further use. The liberated steel is often conveyed to a vibrating screen to further separate any remaining rubber. A second drum magnet helps ensure that any residual steel is captured. This process leaves behind clean rubber, typically ranging from 1 to 3/4 of an inch in size. This material can be dyed and used as mulch or playground cover, or it can be further processed into smaller granulates. Meanwhile, the clean steel can be sold as a high-grade material for various industrial applications, providing an additional revenue stream for recyclers. In the third stage of tire recycling, the clean, wire-free rubber undergoes further size reduction, granulation, and fiber removal. The granulator is responsible for reducing the rubber into granules, typically ranging in size from 1 to 8 millimeters, depending on the specific requirements of the market. As the rubber is granulated, it is discharged onto a vibratory screen, which helps to separate any remaining nylon fibers from the rubber. The screen agitates the rubber, causing the fibers to rise to the top while the rubber granules fall through. The fibers form into fluffy balls, which are then removed using a vacuum system. This system pulls the fluff through ductwork and out to a dust collection system, where it is filtered and collected for disposal. At this stage, The granulated rubber is screened for size and passed under magnets to ensure that any small steel fragments are removed. The cleaned rubber can now be used in various applications, such as field turf, playground surfaces, or poured-in-place surfacing. Alternatively, it can be further processed into fine rubber powders. The final stage of tire recycling involves milling the crumb rubber into fine powders and screening it to meet specific size requirements. The granulated rubber is fed into a cracker mill, which uses two serrated hardened rolls positioned very closely together to crack and mill the rubber into smaller particles. This process generates heat, so a chiller is used to keep the machine cool. The milled rubber is screened using a gyrating screen system with multiple levels of sieves, each containing different mesh sizes. This allows the processor to produce rubber powders of varying sizes, depending on the needs of the end-use market. For example, a processor may produce 30 mesh rubber powder, which is commonly used in rubberized asphalt or molded rubber products. The final step of the process involves removing any remaining fiber or steel from the milled rubber using magnets and vacuums. The resulting powder is then collected in super sacks, ready for sale. These powders are used in a variety of applications, including automotive parts, rubber lumber, rubber mats, and more. The tire manufacturing process begins with mixing. Next is calendaring, where the rubber is rolled into thin sheets and combined with textiles or steel cords for strength and flexibility. In extrusion, rubber is shaped into specific profiles for treads or sidewalls. In the belt and bead manufacturing stage, steel belts are prepared and formed into layers that will reinforce the tire structure. Beads, made from steel wire, are also manufactured here, ensuring the tire maintains a tight seal with the rim. The tire assembly happens on the Max Tire building machine, an advanced, fully automated system. This machine layers the various components, including the inner liner, body plies, belts, and tread, to create a green tire, an uncured tire. Finally, in the curing process, the green tires are placed in molds and heated to high temperatures. This vulcanizes the rubber, transforming it into the final durable product with its distinctive tread pattern. The fully automated workflow guarantees precision at every step, with integrated sensors and real-time monitoring ensuring consistent quality. Mechanical concrete represents a revolutionary shift in road construction technology by using waste auto tires to create an aggregate confinement system that significantly strengthens road foundations. Developed by civil engineer Sam Bonasso, this technology utilizes tire-derived cylinders made by removing the sidewalls from waste tires and filling them with granular aggregate materials, such as crushed stone. The result is a durable and environmentally friendly road foundation that can support immense weight, up to 80,000 pounds, reducing road maintenance by as much as 75%. The key innovation lies in the simplicity of the concept. Normally, roads rely on compacted stone aggregate, which weakens when wet. Under pressure, the stone particles spread laterally, leading to road damage such as potholes, rutting, and edge collapse. Mechanical concrete, on the other hand, uses the rubber tire-derived cylinder to prevent this lateral movement, effectively locking the stone aggregate in place. This creates a road base that is 3 times stronger than conventional methods. The technology is versatile, permeable, and even works underwater, making it ideal for diverse environmental conditions. Compared to traditional geosynthetic confinement technologies, which are more expensive and prone to damage, mechanical concrete is a low-cost, low-maintenance alternative. Its use of recycled tires not only provides a solution to waste tire disposal but also creates a robust and dependable construction material. The system has earned awards from the American Society of Civil Engineers and is patented in both the US and Canada. In essence, mechanical concrete changes the way roads are built and maintained, offering a sustainable and more resilient alternative to conventional construction. This innovation has the potential to transform industrial road maintenance by reducing costs, increasing durability, and providing an environmentally responsible solution.
The Miller M8800 slipform machine continuously pours the single-slope median barrier. Concrete is fed into the machine, which shapes and compacts the barrier as it moves forward along the roadway, ensuring uniformity and structural integrity. The piling process begins with positioning the piling rig at the designated location. Next, a prefabricated concrete or steel pile is lifted vertically by the rig's crane and aligned precisely over the marked spot. The pile is then driven into the ground using a vibration system. The rig continues to drive the pile until it reaches the required depth or load-bearing resistance. Throughout the process, alignment and depth are carefully monitored. If necessary, the pile head is trimmed to the correct level. The rig then moves to the next location, and the sequence is repeated until all piles are installed as per the foundation plan. The construction of the North Manama Causeway involves several key steps. First, cast-in-place concrete piles were drilled and reinforced to form stable foundations. These were topped with pile caps and reinforced concrete piers. Bearings were installed on each pier to allow controlled movement. Precast bridge segments were produced using the short-line casting method, match cast for precision, and transported to the site. Segments were lifted into place using cranes or launching girders, then joined with epoxy and tensioned with steel tendons in balanced cantilever fashion. Link slabs connected cantilevers. Traffic was managed in 9 stages, and strict quality, safety, and environmental controls were enforced throughout. The Veractered Bosenleggers, VBL, efficiently picks up, moves, and lays pipes, specifically designed for excavators weighing 12 tons or more, and pipes with diameters starting from 300 millimeters. The process begins with the VBL grabbing the pipe using its adjustable pin, available in lengths of 1400 and 1800 millimeters. The pin is coated with replaceable plastic wear parts to prevent damage. After positioning the pipe, it is laid in place, ensuring safety and precision. The VBL's durable Hardock steel construction ensures long-lasting performance. It is compatible with the Veractert CW quick change system, and other attachments can be easily fitted through a smart bolt design. The Johnston Vermont 650 operates with independently controlled channel brushes, a wide sweep brush, and a powerful suction nozzle. In dual sweep mode, it clears a 3.6-meter path. Debris is guided by the swiveling broom into the vacuum nozzle, then into the hopper via a straight-line airflow. Water recirculation and internal spray nozzles minimize dust. A high-pressure system enables jet washing. The optional Wonder Hose handles bulky items, while the cyclone airflow and mesh filters capture fine particles. In-cab controls manage sweeping and dumping functions, with automated lifting at junctions. The hopper empties completely via a high-angle rear door and built-in gradient floor. The H25 IVC by Werwe was used on the A44 for rock crushing and compaction. Equipped with 150 heavy-duty picks, the crusher drum breaks down even meter-sized rocks. The machine then compacts the crushed material in the same pass. Thanks to a quick-change tool holder system, different tools can be mounted, allowing flexible use across road and earthworks, as well as in tunnel and rock construction. This enables efficient processing and stabilization of challenging terrain. The Grove GHC 130 assembly features a fully self-rigging design, streamlining setup and operation on the job site. Its frame-mounted hydraulic jacks allow for easy transportation and quick track assembly, enabling fast deployment with minimal effort. The system incorporates two-position hydraulic jacks, providing additional clearance for varying trailer heights, ensuring flexibility in transport. The trackside frame holder and hydraulic clamping system enable rapid and secure attachment to the car body frame, making assembly quick and efficient. Hydraulic connections for the trackside frames are equipped with quick connections that supply flow to the powerful two-stage traction motor, facilitating smooth operation and enhanced performance. The counterweight system consists of 5 pieces, 1 base plate with lifting lugs, and 4 interchangeable slabs, allowing for easy adjustment of weight distribution. The counterweight lifting cylinders and chains are pinned to the base plate, enabling safe and efficient installation of the counterweight. Hydraulic locking pins are used to secure the counterweight to the upper carriage, ensuring it remains firmly in place during operation. This robust assembly process enhances safety and stability, making the GHC 130 ideal for a wide range of lifting tasks. With its modular design and quick assembly features, the GHC 130 offers optimal performance and efficiency on the job site. The CAT 390D 30-meter long front excavator is used for precise demolition in urban areas. The machine dismantles buildings from top to bottom, with debris sorted for recycling. Workers spray water to minimize dust, ensuring minimal disruption to the environment while maintaining control throughout the process. The demolition process begins with the Brock 160, a powerful machine equipped with a BRH hammer and a pincers attachment. It efficiently breaks down concrete floors, ensuring precision and safety. The compact design of the Brock 160 allows it to navigate tight spaces, while its robust performance ensures fast and effective demolition. Every action is carefully executed, with the operator controlling the machine remotely to ensure maximum safety and efficiency. This method allows for swift removal of materials, preparing the site for the next stage of construction. The demolition of the old Kosciuszko Bridge in New York City is a key project, where the Indico ISS 4590ths plays a crucial role. This powerful machine is used to cut through the steel structure, dismantling it piece by piece. With its advanced technology and robust design, it ensures precision and safety during the demolition process. The combination of skill and high-performance equipment allows for the efficient removal of materials, preparing the site for the next phase of construction. This efficient process significantly speeds up the demolition timeline. The production process of Bertin vacuum extruders begins with the preparation of clay, which is previously homogenized and processed by machines such as feeders, disintegrators, and mixers. Once the clay is ready, it is fed into the extruder system. The EB295 and EB460 extruders are designed to optimize the extrusion of ceramic blocks or batons for tile pressing, with high precision and quality. The process starts in the mixing chamber, where two shafts equipped with high durability hammers push the clay through a perforated grid. This grid is part of a vacuum chamber that removes all air from the mass using a vacuum pump. This air removal is critical for enhancing the density, elasticity, and final strength of the ceramic product. After de-airing, the clay is directed into the extrusion screw, known as the caracol. This screw drives the clay through a mold or die, shaping it into its final profile. The vacuum chamber extends throughout the extrusion system in the monoblock models, further ensuring complete air extraction. The extruders are built with high-strength steel sheets and reinforced welded profiles. Gearboxes and shafts are made of alloy steel, with oversized bearings and hardened helical gears for durability. The entire system uses forced oil lubrication and is driven by a pneumatic clutch. Safety guards are installed around pulleys and critical moving parts. Monoblock extruders, EMB 350 and EMB 450, feature an integrated mixing and extrusion system. These models allow processing of low-moisture clay, improving drying efficiency and product finish. Designed for productions from 15 to 35 tons per hour, these machines are renowned for their high productivity, low energy consumption, and long service life thanks to protective linings and easy maintenance. Giant Group follows a highly advanced and innovative production process to create premium performance bicycles. The journey begins in the loom room, where raw carbon fiber threads are expertly woven into durable, lightweight composite sheets. These sheets serve as the foundational material for Giant's top-tier frames, offering an ideal combination of strength, stiffness, and weight efficiency. The next step takes place in the layup room, a climate-controlled environment where over 500 individual carbon swatches are precisely cut and hand-laid by skilled technicians. Each swatch is carefully arranged in a specific sequence, forming what's referred to as a soft frame. The technicians follow strict templates to ensure structural consistency and frame geometry. This stage is both meticulous and labor-intensive, as it plays a crucial role in determining the final bike's performance characteristics. Once the layup is complete, the unfinished frame is moved to the molding department. It is placed inside a preformed steel mold and transferred to a high-temperature oven. During this process, heat and internal pressure bond the resin and carbon layers together, creating a single, solid structure. This transforms the soft layup into a rigid and durable bicycle frame. Following molding, the frame is cleaned, sanded, and inspected. In the finishing section, it is painted, labeled with decals, and coated with protective layers. Riders may also customize frames with their preferred designs through Giant's in-house customization service. In the assembly line, technicians install essential components such as drivetrains, wheels, forks, brakes, handlebars, and saddles. Every part is fitted and adjusted to meet Giant's strict safety and quality standards. For e-bikes, smart systems and batteries are integrated at this stage. Finally, the bicycle undergoes final inspection. A total of 32 pairs of hands and 14 distinct quality checks ensure that each bike is flawless. From raw carbon to a finished TCR Advanced SL, the process takes about 9 hours. This comprehensive manufacturing workflow, starting from raw carbon fiber weaving, precision layup, thermal pressure molding, surface finishing, component assembly, and ending with multi-point quality inspection, ensures that every group bicycle meets stringent performance, durability, and safety standards before being delivered to riders worldwide. The construction of the Watermark rail line progressed systematically over 4 days, with each stage building upon the previous one to ensure a seamless outcome. To begin with, on Tuesday, crews mobilized to the site with all necessary equipment. Initially, the existing track infrastructure was carefully dismantled. This included removing the old rails, sleepers, and ballast. As a result, the track bed was cleared and made ready for new installations. Subsequently, on Wednesday, attention shifted to preparing the subgrade. The ground was leveled and compacted thoroughly to establish a firm and stable foundation. Moreover, geotextile layers were installed to enhance soil integrity and facilitate drainage. Once this was complete, fresh ballast was evenly distributed across the track bed to form a solid base. Following that, on Thursday, new concrete sleepers were laid with precision. The rails were then positioned and fastened atop the sleepers. In addition, welding crews worked to join the rails seamlessly, while alignment checks ensured the track met technical specifications. This phase was essential for achieving structural accuracy and long-term performance. Finally, on Friday, the focus turned to quality control. The newly installed track underwent detailed inspections, including measurements for alignment, elevation, and gauge. Furthermore, ballast was tamped around the sleepers to lock them in place and improve drainage. Alongside this, signaling systems were tested and finalized. Consequently, the rail line was certified as operationally ready. The AMS 200 rail welding machine is a state-of-the-art mobile solution designed for rail track repair. This new generation machine combines the distressing and flash butt welding processes into a single operation, eliminating the need for additional pulling devices. With the necessary force to achieve precise dilatation, the welding machine accounts for material loss during welding, ensuring accurate results. Its long travel capability allows for reliable distressing, even in low temperatures. The machine is equipped with an integrated deburring unit which removes burrs immediately after welding while keeping the rail ends securely clamped. By applying distressing force in the rail's neutral zone, the welding machine enhances weld quality and protects the machine from unnecessary stress. The design ensures that there is ample space around the rail foot, preventing collisions with sleepers and track fasteners, and reducing the need to raise rail ends. Available in 2 system variants, the Super RoadFlex model provides high flexibility, making it ideal for road/rail operations. This innovative design ensures optimal performance, even in the most challenging environments, enhancing the efficiency and durability of track repair processes.
Automation in tire building technology plays a pivotal role in improving precision, efficiency, and productivity. Modern tire building machines, TBMs, integrate advanced automation to manage the complex assembly of multiple tire components, including the carcass, belt, bead, tread, and sidewall. Automated TBMs are capable of producing up to 200 tires per hour, significantly reducing manual intervention and minimizing errors. In traditional tire manufacturing, the process was labor-intensive, with manual operations accounting for approximately 40 to 50% of the overall production time. Today, automation has reduced human involvement to just 10 to 15%, focusing mostly on quality control and maintenance, leading to an increase in overall consistency and product quality. One key feature of automated tire building machines is the incorporation of robotics and vision systems, which ensure precise placement of components. For example, automatic bead setters and robotic manipulators streamline the assembly process, reducing setup times by 20 to 30% compared to manual systems. This also improves material utilization, leading to a 5 to 10% reduction in waste. Automation is also pivotal in reducing downtime. Real-time monitoring systems enable predictive maintenance, lowering machine failures by 15 to 20%, and boosting overall equipment efficiency, OEE, by as much as 10 to 15%. In terms of labor savings, highly automated plants typically require 50% fewer operators compared to traditional setups, while output remains constant or increases. This transformation in labor deployment has significant economic advantages, especially in regions with high labor costs. Ultimately, automation in tire building technology has transformed the industry, enhancing product uniformity, reducing cycle times, minimizing waste, and increasing plant efficiency, while still ensuring the high-quality standards required in the tire manufacturing industry. Racing tire molds play a critical role in the manufacturing of high-performance tires, especially for motorsports. These molds are typically produced using the injection molding process, a technique favored for its precision and efficiency. In the injection molding process for racing tire molds, the mold is first designed with intricate patterns that define the tire's tread and sidewall features. These patterns are crucial for ensuring optimal grip, durability, and handling during races. Once the mold design is finalized, the injection molding machine heats raw materials, typically a mix of synthetic rubber and other compounds, until they are in a molten state. The molten material is then injected into the mold cavities under high pressure, ensuring it fills every detail of the mold. This precision is vital in racing tires, as even the smallest defect can affect tire performance. The mold is cooled to solidify the rubber into its final shape. After cooling, the mold opens, and the newly formed tire is removed for further processing, such as trimming and inspection. Using injection molding for racing tire molds allows for high production efficiency, consistency in tire quality, and the ability to produce tires with complex and fine tread patterns. The result is a durable and high-performance tire designed to withstand the extreme conditions of competitive racing.
The pioneering Spirit, equipped with its revolutionary jacket lift system, JLS, successfully removed the 8,100-ton Ninian Northern jacket from the northern North Sea. After precise cuts through the jacket's 8 legs, the vessel's JLS lifted the structure, ensuring its safety and integrity. This advanced technology allowed for the direct transfer of the jacket to the Shetlands for recycling. The project showcases the vessel's capabilities, completing one of the heaviest offshore jacket lifts ever, demonstrating its role in transforming offshore operations. Watch the cleaning process of stern drives on a Regal 29 boat using a high-pressure water jet. This method effectively removes buildup and debris, ensuring your boat stays in top condition for a safer and more enjoyable experience on the water. The propeller cleaning process using the cavit cleaner system begins with positioning the diver near the heavily fouled propeller. The diver holds the cavit cleaner cleaning tool, which operates with cavitation technology that creates microbubbles collapsing on the surface, effectively removing marine growth without damaging the metal. The diver starts cleaning one blade at a time, maintaining steady movements to cover the entire surface. The tool is passed along the blade's edge, then gradually works toward the center. Layers of biofouling, such as algae and barnacles, are visibly stripped away within seconds, exposing the original metal surface. The cleaning continues in smooth, overlapping passes to ensure complete removal of the vegetative incrustation. Thanks to the non-abrasive nature of the cavitation process, the propeller remains intact with no scratches or structural impact. After completing one blade, the diver moves on to the next, repeating the same methodical process. The water around the propeller becomes murky due to the released debris, but the cleaned areas are immediately visible and shiny. Within approximately 3 minutes, the diver successfully restores the entire propeller to a clean condition. The Taylor TEEC 207 is shown efficiently handling empty containers in a port environment. The operator first positions the side-mounted attachment to grip an empty container, using guide arms and rear twist locks to secure it. Once locked, the 63 feet UltraView telescopic mast lifts the container smoothly. Thanks to its 24-inch side shift feature, the container is precisely aligned and stacked up to 8 units high. After placing one, the handler reverses and repeats the process with the next. Its heavy-duty frame, stable wheelbase, and hydrostatic steering enable easy movement even in tight spaces. The elevated cab includes a multi-function joystick, 7-inch touchscreen, and wide-angle mirrors, offering excellent visibility and control. LED work lights and twist-lock signal lights ensure safety. The diamond wire saw machine drills holes to insert the wire, which is then threaded around the stone. The wire, embedded with diamond segments, moves continuously at high speed. Water is sprayed to cool and reduce dust. The wire gradually cuts through the stone, enabling precise block extraction from the quarry. The process of making brushes using the Bresson Mechanical Projects brush-making machine, operated manually, begins with feeding the bristle material into the machine. The bristles are aligned and cut to the required length. A metal wire or similar material is used to hold the bristles together at one end. Then, the worker rotates the machine's handle by hand to twist the bristles tightly together. This action forms a solid and uniform brush head. After twisting, the brush is inspected to ensure good quality and proper formation. Sugarcane bagasse tableware is made by collecting bagasse, sugarcane fiber, cleaning and pulping it, then molding it under heat and pressure into plates or bowls, followed by drying, trimming, and sterilizing for final packaging.